using the mirror equation and the magnification equation. Now I'm going to show you a simulation that you can play around with yourself. I have a link to the simulation in your folder for this unit. But I'm going to show you a simulation that helps you to see what's happening when you have an object a particular distance from a mirror. Where is the image formed? What does it look like? What's the height of the image compared to the object? So the first thing I want to do with this video clip is talk about some important terms. First of all, you need to know that this is a concave mirror. You can see that up here. It's concave because the light is hitting the bowl side, the inside of the bowl side. So it's curved this way. It's curved toward the object, if you will. And also this notation over here, I'm underlining with the cursor, DO, the object distance, is greater than 2 focal lengths. So what does that mean? Well, here's the focus. Here's the focal point, and that focal point is located 4 centimeters, I suppose, from the mirror. So 4 is the focal length. So 2 focal lengths would be 8, and that CC means center of curvature. The 2 focal length distance is the center of curvature. In other words, if we extended this mirror in a complete circle, this point right here, the center of curvature, would be the center of that circle. So that is 2 focal lengths away from the mirror. Our object is way out here, right? Way more than 2 focal lengths away. You can see down here, it's 13 centimeters away from the mirror. So that is our object distance. DO is 13. Center of curvature is 8, 2 focal lengths from the mirror. The focal point is 4 from the mirror. So the focal length is 4. So those are some important terms you need to know. Now, the image that is located, that is formed when this object is here for this particular mirror, is located right here. And you can see a few things over on this side. You can see that the image distance is measured from the mirror. You can see it's just short of 6. They have it at 5.78. You can verify that using the mirror equation. You can see that it is an inverted image. You see that it is upside down. It is a real image. Now, it's a real image for 2 reasons. Number one, it's a real image because it's upside down. All upside down images are real. All real images are upside down. But the true definition of a real image is this. It is the point where 2 reflected light rays intersect. That is where you get a real image, the point where 2 reflected light rays intersect. And you can see from this object, 1 light ray travels in this way, hits the mirror, and reflects out along this path. And 1 light ray travels in this way. All right, oops, I'm sorry, wrong one. 1 light ray travels in this way and reflects out along this path. So those 2 reflected light rays intersect at this point. All right, so that's why that's where the image is. And since actual light rays intersect, we call it a real image. And you can see that the image is smaller than the object, and that's shown here. The object height is 2. The image height is 0.89. That negative sign just means that it's upside down, that it's inverted. You can see that the image height is less than the object height, and you can see that the image is located between the focal point and 2 focal points, the center of curvature. So it's going to be somewhere in there. All right. The next video clip, we will take a look at what happens when you start to move this object closer to the mirror. But feel free to rewatch this one if you need to review any of the terminology involving object distance or image distance or focal length or where the center of curvature is and how we know that's a real inverted image.